All right, you guys, I'm glad you came back for the last few slides. This should be the fun stuff, but we'll hopefully really tie things together. So we just finished off with, we were looking at cone opponency, and I was showing you after images. The after images were cone opponent to the images that you'd been staring at for 30 seconds previously. So let's talk a little bit about color blindness, and then we'll come back to the other aspects of vision, constancy, and assimilation. But first, let's talk about protanopes and deuteranopes. So individuals with protanopy are missing the long wavelength sensitive opsin, and I'd ask you to remind me where those are expressed, and you would tell me those are expressed in the red cones. And individuals with deuteranopy are missing the medium wavelength sensitive opsin, and you would remind me that those are expressed in the green cones. And the proximity of these two genes, the long wavelength and medium wavelength sensitive opsin on the X chromosome, their location on the X chromosome, predisposes them to crossover, homologous crossover during meiosis. And I'm not going to test you on meiosis in this course, but hopefully you recall that homologous crossover does occur during meiosis to promote genetic shuffling as gametes are being produced. And so, of course, females, individuals who are biologically female, have two X chromosomes. So even if they're missing one of these opsins, they have a backup copy on the other X chromosome. Males, individuals who are biologically male, have an X chromosome and a Y chromosome. So if their X chromosome is missing one or the other of these, they don't have a backup copy, and so the condition will manifest. And it manifests if this is a normal palette that someone with normal vision can see, then the panel in the middle is showing a panel for somebody who has protanopy or deuteranopy and is missing the long wavelength sensitive or medium wavelength sensitive opsin. Blues are fine, blues over here, but there's an inability to distinguish between reds and greens, all of which appear as some variant of maybe brown or beige or yellow. And that's not uncommon, depending on which ethnic population you look at. And I think this will probably be northern, western, European white males will be this number, and that number will vary in different ethnic populations. But reliably, it is more prevalent in males than females because it is an X-linked condition. And this is much more rare. Individuals who are tritanopes or have tritanopy are missing the short wavelength sensitive opsin. That's not X-linked. It is on chromosome 7, and you can fact check me, but I'm pretty sure the short wavelength sensitive opsin is expressed on chromosome 7, and in any case, it's not sex-linked. And so it is a recessive autosomal condition, right? It's not sex-linked, it's on autosomal, and you need to either be missing both or have two bad copies. So that would be autosomal recessive, right? Little r, little r. If you have big R, little r, you're fine. But if you have little r, on an autosomal chromosome, that would be a fairly rare combination. So I can't give you an exact number, but suffice to say it's extremely rare, and this is what the color palette might look like, right? So it's the blue cones that are impacted because the short wavelength sensitive opsin is absent, and so lots of reds and pinks and maybe browns and shades of blue, but losing out on the distinction specifically between the greens and yellows and reds. Because you only have two opsins left, which are the medium wavelength and long wavelength, respectively. So I don't know if you can click on this. I've had to fix this link a couple of times, but in any case, I'll post it for you in the interesting links and helpful files module. And take a few minutes and do the Ishihara color vision test and see if you have any indication that you may fit into one of these categories. I'll post that for you, or I'll check that it's already been posted. Okay, constancy. So in the first part of this lecture, we said constancy. I used the example of wearing a red sweater in the lecture hall and wearing a red sweater in a dark movie theater and your ability to determine that my sweater was red regardless of the ambient lighting is usually pretty good. So let's take a look at constancy. If we look over here at this, let's just call it a Rubik's Cube. It's not quite a Rubik's Cube, but it looks something like a Rubik's Cube. And in this, what looks like maybe morning light, yellow light, you would tell me that this square over here is which color? And hopefully you're agreeing with everybody else and suggesting that this is blue, right? I would argue that I perceive this particular square as blue. And if we go over here, we've got more evening light, certainly a different type of luminescence. And over here, you would maybe argue and tell me that this square is yellow, and I would agree with you. I perceive this as yellow compared to the neighboring squares in this type of ambient lighting. But hopefully you'll agree with me that if you were to cut these two squares out, right, print the slide, print out your slides in color and cut these out. So you take them away from the ambient lighting that you perceive, put this square beside this square when you've cut it out, and they are the exact same shade of gray. And if you look more closely at this slide now, hopefully you'll see that, yeah, actually, this is gray, and this is gray too, and they're the exact same color, even though when we're presented in this shading, in this ambient light, we might perceive this as blue, and we might perceive this as yellow. So that demonstrates constancy. It also demonstrates a failure in constancy, because even though this square is gray, we're not perceiving it as gray, at least initially. We're perceiving it as blue or yellow. So in this instance, particularly when we are unsure about the ambient lighting, or we're relying on unconscious assumptions our brains are making about the ambient lighting, constancy can fail. So we're usually pretty good, red sweater example, but sometimes we fail, this example. All right, so this is more fun in lecture because we had the opportunity to do this in West Mall Complex earlier in the term, and if I recall, there was something like half or a little more of us that were, or half or a little more of you, that see this as black and blue, and then there was maybe half or a little less, maybe closer to a third of us, including me, that see this reliably as yellow and gold, and that remains true. I'm looking at the slide in front of me, and it is yellow and gold. You may be seeing black and blue, you may be seeing brown and beige, right? You may fit into one of those other categories that sometimes come up. So this is another example where constancy fails. So there has been a significant amount of valid, high caliber scientific literature into the dress and why individuals perceive the dress as different colors. So I've posted 2 papers for you. I don't expect you to read through them in entirety, but they are interesting, and I've summarized the findings for you here. I won't read this to you because that wouldn't be an effective use of time. You can read through this yourself. This was published in Current Biology, which is a top-tier scientific research journal. Up there, maybe just under Nature, Science, and Cell, you'll find Current Biology. Okay, so the summary findings, I'll let you read this. I won't read it to you, but the summary findings are over here, and I've given you the kind of the Coles notes here. So one reason why most individuals see the dress as black or blue compared to white or gold is due to this being an alternative forced choice. So very often when studies are done, people are asked, do you see black and blue or do you see white and gold? So right away you're put in one of 2 categories. You have to see A, or do you see A or do you see B? There's no other option. So that could be one reason why people see A or B instead of maybe C, D, or E, which they might see if they weren't given an alternate forced choice. It's been shown that white and gold is higher in females, particularly females who are older. So individuals who are older and individuals who are female tend to see white and gold. And then the opposite is true. Black and blue is higher in individuals that are younger and individuals who are male. So that might explain why 2/3 of our class, right? We were in line with this. You guys are relatively young, and some of you are male, and so that might account for the higher proportion of black and blue perception in our class. It's also been shown that assumptions are made about the level of illumination. And we said that the illumination, the type of illumination, is important for constancy or the failure of constancy. So individuals who see white and gold favor or see or assume a cool illuminance, say a blue sky in the morning light. Whereas individuals who see black and blue tend to favor or perceive a warm illuminant, such as maybe under a spotlight entering a party on a red carpet in the evening. So the assumptions that your brain, with or without your conscious input, the assumptions that your brain makes about the illuminant is what determines largely white and gold versus black and blue. Okay, so I've italicized that for you here. It's implicit assumptions about illumination. That's most important. Is there some hard wiring? Well, twins tend to see the same colors, so there may be some underlying genetic component. And white and gold, individuals who see white and gold, one study measured the pupil sizes and the optical pigment levels. And so physical differences or anatomical differences in the eyes may account for the amount of light entering the eye, how light acts within the eye if pigment is involved, and therefore might influence the implicit assumptions that are made. Certainly, there are a number of age-related changes that occur in the eye, and without going into any one specific, we know that there's a difference between older and younger individuals, so that could be related to changes that occur with time. And so the question, why this particular photo? Are there other photos that can elicit this differential response from individual to individual? And I'll show you in a minute. It appears that is in fact true. This particular photo, it just seems to be the way the light captured the dress in the photo. If you see the light under normal white light, just a white background here, there's no misinformation about the ambient light. I imagine that all of you now see the dress in its true colors, shall we say. The dress is black and blue. Okay, so if we were in lecture, I would ask you what you see here. And this is reliably fun. Some of you are going to say black and gold. Some of you are going to say blue and white. And some of you are going to say green and brown. And some of you are going to say, what? Because we're not really doing this in class, so you can only see what you see. But in my experience, having taught this and showed this slide a bunch of times, it's black and blue, green and brown, or green and gold, and black and brown, or black and gold. And so it's not just the dress. Now the jacket is a thing too, and you'd have to Google this. I don't actually know what color this one is. I know what I see, which is baby blue and white, but that might be different from what you see. So we'll have to Google to find out what color this actually is. So it's not just the dress. This ambient lighting can fool us in a number of different types of photographs. All right, assimilation. So we said this is a tendency of one color to take on hints or hues of another color that it's juxtaposed or side by side with. So hopefully you'll agree with me. If I were to ask you what color best describes the sea here, you might say some shade of blue or light blue. And then if I asked you what shade describes this, the L here, and you'd say maybe some kind of light green or greenish. Hopefully you agree. And then if I asked you to distinguish or describe these two O's here, you might say that this is more of a blood orange and this is more of a light orange. And then now if we take a closer look, in fact, the C and the L are the exact same shade shown over here, the light green or sea green. This sea green and this sea green are exactly the same color. And I know that's hard to believe because of assimilation. Okay, they're taking on hues of the color that they're juxtaposed with. And so it looks like two different colors when it's actually not. Again, print out the slide, use a pair of scissors, cut out a color square from over here and over here and put them side by side, and they will be the exact same color, sea green, as hard as that might be to believe. Likewise, both of the O's are the exact same color shown up here. The same shade, kind of middle of the road orange, even though here they appear darker and lighter because of the colors they're juxtaposed with. Cut them out, prove it to yourself. They're both the same shade of middle of the road orange. So hopefully that demonstrates assimilation, right? The third aspect of vision that we talked about, where colors tend to take on hues of other shades or colors that they're juxtaposed or side by side with. So make sure you're clear on cone opponency, constancy, and assimilation as three key aspects of color vision. And then I'll leave you with some review questions. Please stay inside if you possibly can. Please practice social distancing if you must go out. And please stay safe, and I'll see you, or you'll hear me for another lecture tomorrow. And I will have office hours very soon. I've sorted out Zoom, I think, so hopefully we can have some face-to-face time for office hours. I'll see you soon. Stay safe.